Hello and welcome back. We're going to move on with our second video lecture on chapter 14 on the same topic, acids and bases. And in this chapter, we're going to be covering pretty much just calculations of the pH values for different strengths of acids. We'll look at strong acid and weak acid. So let's begin to focus on the solution components and their chemistry. So when you are doing calculations, we have to consider carefully the type of equilibrium that these types of acid, whether strong or weak acids, undergo, and keep in mind the species that are present in the solution. So here we are going to be looking at an acid and work out what are the species that are formed when an acid is in solution. Let's take an example here. If to calculate the pH of 0.1 mole of HNO3. Now if you look at this, HNO3 is a strong acid. So what did we learn from the strong acid in the previous lecture? Strong acid dissociates completely. So in other words, when you are looking at a strong acid, the concentration of the acid will be pretty much the same as the concentration of H+. That is the concentration of H+ when it dissociates in solution. Now let's look at that. Since HNO3 is strong acid, the major species will be H+, NO3, and H2O. Why H2O? Because this is in aqueous, so it's in water. Water is still a dominating species. Now, there won't be any of this original acid, which is in a molecular form. It'll be all completely ionized. That's what we know in a strong acid. So that's what it is. The molecular acid is virtually zero, and the acid is completely ionized in water, which says completely dissociates in water. So the OH concentration will be very small because the only contribution from OH comes from water, and that's already a very small quantity. That's what the water contribution shown in this equilibrium. So this OH will be very small compared to the H+ that is coming from the acid. So in this, this is an acidic solution where H+ is greater than OH. So OH will be even lower than -7. So let's look at the calculation here. H+ from NO3 will be 0.1 molar. H+ from H2O, we know that can be calculated. From H2O, we know approximately that's about 10 to the -7. That's very small. That's very small compared to the 0.1. So that virtually can be ignored. Since the dissolved HNO3 is the only component, main component of H+, so we can work out the pH. So using the concentration, H+ is 0.1 molar, so pH is minus log of 0.1, which is 1. So that's the pH value of the acid. Now the second example, you will see that we asked to work out the concentration, the pH of HCl, which is also a strong acid, but one thing that we have to bear in mind, the pH of pure water is 7, and the concentration that we are given in this acid, HCl, let me go back to the question here. Way back. Sorry about this. Here. You see this value here? 1.0 times 10 to the power minus 10. this is even smaller than the concentration of hydrogen ions in water. So in other words, if you're calculating the pH of this very small concentration of HCl, it is going to be very negligible. I mean, 10 to the minus 7 molar is H plus from water, normal water. So in other words, this is way smaller. In other words, the contribution of the H plus predominantly is coming from water instead of HCl because it is so small. Okay, so that won't be critical in our calculation. Let's go to the slides. Now you see here, in the determination of weak acid, it's quite different when we are looking at the calculation. Here it takes several steps, and we're going to run through these steps. Let me just go through this series of steps. Number one, list the major species and choose the species that are present that can produce H+. Write the balanced equation for the reaction. Using the values of equilibrium constant for the reaction, decide which equilibrium will dominate in producing H+, and then write the equilibrium expression of the dominant equilibrium and list the initial concentration of the species. Define the change, write the equilibrium concentration in terms of the change, and then substitute into the equilibrium expression. Then you solve. So in other words, majority of the steps that I've mentioned in that previous numbers is actually setting up the ICE table. So I'll go through that in here, and you will see now that we are beginning to apply the notion of this ICE more and more as we solve this problem. Now, one of the steps that we are going to bring in is this. You notice that in the last last chapter, we were talking about the value of x to be very small, meaning that we can simplify the equation if we have the x value to be small. And that's what we are seeing in here. We make an assumption where x is very small, therefore initial concentration of the acid minus x will be approximately the same as the initial concentration. That is what we expect in a weak acid. So this is going to be a very, very important step. In fact, it is a lifesaver. I say it's a lifesaver because it makes our problem a lot easier to handle mathematically. All right, so now let's look at one problem, and that is this one. Hypochlorous acid has got the Ka value of 3.5 times 10 to the power minus 8, and it says calculate the pH of 0.1 molar of this hypochlorous acid. Again, let me emphasize, it is a weak acid. How can we tell it's a weak acid? It's a very small K value. So you can see here minus 8, 10 to the minus 8. Okay, we'll list the major species. So if HOCl is a weak acid, the major species will be HOCl. And the other major species would be water. H plus will not be, because H plus will be only a partial quantity dissociated. And likewise, its conjugate base, which is OCl minus. OCl minus will be very small, as we know that dissociation of weak acid is very small. So both species can produce H plus, and that is from the hypochlorous acid and also from water. So notice the two. This is the Ka of the hypochlorous acid, and this is the Kw of water. All right, so now what we can do is make this determination. Step number 3. HOCl is significantly stronger than water, so it will dominate. So in other words, we don't have to worry about the water contribution. So we'll leave the equilibrium of water alone and focus on HOCl. So we can now use this expression here. 3.5 times 10 to the power of minus 8. Okay, I have to make one correction here. Please apologize for this. This should be minus 8. Sorry for that mistake. Okay, let's go back. So Ka, 3.5 times 10 to the minus 8, that's the K expression, the ionic products over the acid. And now let's do the initial concentration values. Is 0.1 molar of the hypochlorous acid, 0 of the OCl, 0 of the H+. We're assuming that we are neglecting that contribution from water, remember. So now we let X be the amount that dissociate to reach equilibrium or in reaching equilibrium, and then we can write the equilibrium concentrations in terms of X. So notice that HOCl will be 0.1 minus X, OCl will be X, and so as H plus will be X. So it looks like this in the ICE table. That's the equilibrium. Now let me change my mistake here, 10 to the minus 8, and then write the initial 0.1 molar, 0 and 0. Change is minus X, plus X, plus X. Equilibrium will be 0.1 minus X, X, and X. So now we can set this up into the equilibrium constant. So it will be X multiplied by X over 0.1 minus X. All right, so this comes from the equilibrium calculation or equilibrium expression. Now you can look at this step, number 9. Since K is so small, we can expect a small value of X. Why is so small? This minus 8, 10 to the minus 8. Thus, we make the approximation HA0, which is the initial acid concentration minus X, is equal to HA0. That essentially means you can simplify this denominator. So how does it look? Here, you see that? You remove this X term, and it'll be X squared over 0.1. X squared over 0.1 is equal to this. That makes the mathematical calculation very simple. That's why I call it the lifesaver. So solve that, and it gives you that value of X. That makes a very complex problem simple, and it works in many of our examples. And you should learn that and make sure you follow that step very well. Now, when you make this determination, there is an approximation that you have taken. That is the approximation of 0.1 minus X is 0.1. It must be validated. What is the criteria? The criteria is that the value should be less than 5% of the quantity that we are looking at. So here, let's look at that. X over HA0 times 100. So here will be 5.9 times 10 to the minus 5 over 0.1 times 100. How does that compare? 0.059%. That's less than 0.1. So it's way lower than 5%. So approximation is valid. So anything that is less than 5% with this approximation is fine. And this example clearly shows that. So now we can then do the calculation of the pH, right? So we can calculate the H plus, we got the H plus concentration now, and then we can find the pH. So H plus is 5.9 times 10 to the minus 5, and pH minus log of this value here is 4.3. So that solves that problem for a weak acid. So you can see that in the weak acid, it follows through a multiple set of steps that you carry out. However, we make some very good judgment on the sets of conditions and do the approximation as we've come to the final step, and we get the answer. And then we have to validate and check that answer to make sure that we are within the range. Okay, let's look at what are the major species present in 0.25 molar solutions of each of the following acids. Now look at these acids. You have to be familiar with the type of these acids, whether it's strong or weak. So these two here, HNO2 and CH3CO2H, which is, this is acetic acid, this is nitrous acid. Nitrous acid is a weak acid. Acetic acid is a weak acid. So they are both weak acid. And that means the major species will be the original acid and water. So here, the major species will be the original acid and water. And how do you calculate the pH? You have to follow setting up the ICE table as we have done in the previous example. So I'd like you to try it out and verify these values that are given in here. Okay, I'll give you another different type of example here. You are given two acids. Look at this. You have hydrocyanic acid and nitrous acid. So here you're given 1 molar of hydrocyanic acid and you're given 5 molar of nitrous acid. Now, when you're given this, you first compare the equilibrium constant of these acids. The reason is that it'll determine what sort of strength and the sort of equilibrium you will be expecting. Not so much of the concentration. You can look at the concentration later. So here, Ka minus 10 to the minus 10. Ka 10 to the minus 4. That's a huge, that is about 6-fold. That is 10 to the 6 difference, which is close to 1 million range difference. So this is a huge difference. This is a very small Ka compared to the HNO2. So when you have a mixture, you have to consider all the equilibrium that are present in that mixture. What are the equilibrium? So these are the equilibrium. Remember that this is a mixture in water, so you have to bring in the water as also part of the equilibrium. So the first one is hydrocyanic, nitrous acid, and then water. Watch these values. These two are much smaller than this one. So how are we going to find out the pH of this? So we will look at the equilibrium and consider the pH that is a dominant species or dominating in these conditions. So if you're going to consider these three equilibria, you will see that this basically will be the equilibrium of significance, because these two will be very small in their contribution, very small compared to this one. So when we come to calculating this problem, we are going to simplify that by just dealing with the dominant, right? So let's look at this species now. That's the Ka value, and that's the Ka expression. So now we can work out the ICE setup for this acid. That's the ICE. So you start with 5 molar, 0 and 0. Remember, we are ignoring the contribution from the other two equilibria. And now this change, minus x, plus x, plus x. And then that's the equilibrium concentration. So now you can solve. When we solve, we use the approximation again to simplify this, and then solve it, and this will be the value of x. Now when you find the value of x, validate it. In other words, always check with a 5% rule whether it is valid. So let's try that 5% rule. X over HNO2 times 100. So substitute the value of x. 0.9. 0.9%, that's lower, much less than 5%. So that's pretty good. So this is acceptable. So we can work out the pH value, and that's the pH. Now, if we want to then follow on with the calculation of the concentration of cyanide ion, yes, we can continue. Now that we have settled the value of the hydrogen ion, we can then use this value to solve for the cyanide concentration. Look at this. The CN ions in this solution come from the dissociation of HCN. So that's the equation. And now we can substitute in the equation. So Ka for that is 6.2 times 10 to the power minus 10. This we've just determined from the HNO2. We're going to use it. And this is the concentration that is given, and we're going to use it. So this is the unknown that we are calculating. So now let's substitute in those values. 4.5 times 10 to the minus 2. And then that's the initial. Then you get this value. So that leads us in a very interesting situation. You see here, you had 3 sort of equilibria, but you took the dominant equilibria to solve for the main species, and that is H+. And then once you have that, you can use the H+ to solve the species of the individual ions of the respective equilibria. Okay. So finally, there is a way of representing weak acids by their percent dissociation. So percent dissociation or percent ionization is the amount dissociated over the initial times 100. And that is something that we can calculate for the weak acid. So calculate the percent dissociation of acetic acid given that Ka value. So essentially we'll follow the same calculations. Okay, follow the same calculations. So set up the ICE table, initial, change, equilibrium, and then solve, find x, and then you'll find x. Once you have the value of x, in this case is 4.2, then we can work out the percent dissociation. Percent dissociation is basically x over the initial, which is 1 times 100. So percent dissociation is x over initial times 100, which is 0.42%. All right, so thank you for listening. That is the second video for chapter 14.